Hey everyone, let me check if you're live. Yes, I think we're live. Really clear the canvas. I need to check my audio so quickly. Okay, I think I'm audible as well. So we'll wait for a couple of minutes to. Yeah, I think people are joining in. Yeah, let me know if my voice is clear to you. If you have some problems, let me know so that I can fix those things. But yeah, let me know if I'm audible properly or you're having some problems hearing me out. And today we'll be solving this problem: uh, how to remove a loop in a linked list. Well, I'm pretty sure that you must have solved this problem as well. Like, it's a very popular interview question. In case you haven't solved it yet, uh, just solve with me today. But if you have solved it, I'm also sure that many of you are there who don't actually understand the proof for the things, right? Or what's the best way to do it, or why, if you're using a slow and fast pointer, why does this actually work, right? I'm not talking about detection of loop, but more importantly, I'm talking about how do you actually remove the loop in a linked list as well. So to clear these things out, see, in an interview definitely you can propose this solution of slow and fast pointers, but the problem there being that a cross question will come that why is it working, right? And if you're unable to answer that, that wouldn't be very good. So yeah, today we'll be solving this problem and we'll understand in details like what are the various ways we can solve this, and also why the solutions are working, right? So before that, let me know, like, can someone let me know in the chat if you can hear me properly or not, or is there some problem? Let me know in the chat once, if you guys can hear me properly. So we'll be doing this problem, and before that, yeah, let me know in the chat if you guys can hear me properly. Actually, no one is typing anything. Yeah, let me see myself. Yeah, I think I'm audible. Let me know if you guys cannot hear me, right? So the problem statement is pretty simple. You have a linked list given to you, and you have to remove if there is a loop in a linked list. Now, the important observation here is that the linked list should be single linked list. It should not be a double linked list, right? Otherwise, it will become a very complicated issue. So, given a linked list of n nodes, such that it may contain a loop here means that the last node of the linked list is connected to a node at position x, and the linked list does not contain any loop, then x equals to 0. So basically, what it means is that you are given a linked list like this 1, 3, 4, right? And if you see the last node 4, the next of 4 is 3, which actually creates a loop, right? It actually creates a loop between 3 and 4. So this is the question. You have to find this loop and you have to remove this loop as well. So let's take an example here. So let's say we have 1, 2, 3, 4, and let's say four's next is 2. So there is a loop, right? There is a loop that is 2, 3, 4. Just see, like, if you go from 2 to 3 to 4, and you will again come back to 2. So there is a loop, and what you have to do is you have to remove this loop. Basically, you have to change this thing to 1, 2, 3, 4, and after this there will be null, right? So you have to change this thing to this thing. So how can we do this, right? The first approach, it will be pretty simple. We'll start simple approach, right? The first approach will be that what you can do is, see, uh, when does a linked list has a loop? When a node is visited again, right? When you have multiple nodes, when you are visiting the same node again, it means that the linked list has a loop. So here, if you see, when you are going, like when you are iterating on the linked list, you're starting at 1. From 1 you are going to 2, right? From 2 you are going to 3. From 3 you are going to 4, and from 4 you are coming back to 2 again. So you are visiting two times, right? So there is a loop, and the loop, the first node that you visit again is the starting point of the linked list, right? The first node that you are visiting again is the starting point of the linked list. So you can maintain, let's say you have some data structure where you are maintaining the nodes that you are visiting, right? Whenever you are visiting a node, you are maintaining that node in this data structure. So you, whenever you are visiting a node, you can quickly check if that node is already there in the data structure. If the node is already there in the data structure, you can just tell that this is this contains a linked list, and to remove it, you have to remove from the previous position. If a node is not there in the data structure, then it is not it is not, still you haven't found the cycle yet, so you can proceed to the next node, right? So the data structure that allows, what should be the proper property of this data structure? We can insert into this data structure, and we can quickly search in this data structure, right? We can insert and quickly search. So any data structure, like it can be a set or it can be a map, all these data structures will work for us, right? They quickly allow us to insert and search for things. So we can use any of these data structures and it will work for us. So let's quickly look into the code for this, like this approach. So okay, so we will just remove the loop without removing any nodes, that's fine. So we'll maintain a data structure, right? So let's maintain a set. uh just maintain a, let's just maintain a set, right? What will be the type of data it is holding? It will be holding the references or the pointers to the nodes that we are visiting. So that's why it will be node star, right? So set node star visited. And what we'll do, we'll maintain a node current, node star current, and we'll start off at head. We'll start off at head. And what do we do here? While current not equals to null, while current of next, let's do current of next not equals to null, right? Well, current of next not equals to null, what we'll do is we'll search, right? First of all, we'll search, or first of all, let's insert to visited dot insert current, and let's search in the let's search something, right? So what will we search? We'll search that if the next node is already visited, right? So if visited dot find visited dot find current of next, if visited dot find current of next not equals to visited dot end, that means it is already like the next node is already visited. In that case, that basically forms the cycle, right? Basically you are at the last node and the next node is already visited, so that will be the first node of the cycle, and you are basically at the last node. So this is the point where you should remove the current this is the point where you should remove the loop. So current of next, you will make it null, you will just make it null. And here, from here you can directly return, right? So from here you can directly return. So this is one of the ways. Let's quickly try to run this. So we'll try to compile and run. We'll see if there's are some issues, and you can definitely use a map here as well. You can mark it to be true and something. So visited but not declared in the scope. It was not declared in the scope, that's fine. Hash include set. Will this work actually? We actually don't need a set. They have given the constraints such, and also if you look into the question, the constraints are set in such a way that this is not accepted, right? So program took more time than expected. Okay, we are not doing current equals to current of next. So we'll continue our loop. So current equals to current of next. Otherwise, it's sticking in an infinite loop. So we'll just continue to the next node. Let me know if it makes sense, and if it doesn't, let me know that as well, so that I can help you out here. So your output is one expected, and we'll submit. I hope this will work. This should work. Okay. Time limit exceeded. Time limit exceeded. Yeah, I think because of the login time limit, it might Please optimize your code. Yes, because of the log n time limit, it is exceeding. That's like log n for the set, right? So we want a order of n complexity. Like if you look into this question, it will tell you that extra time complexity is order of n, space complexity is order of 1. But definitely this is one of the ways to solve this, and you can definitely solve this way first. So this is a very easy solution, intuitive solution. Like you're visiting the same node again, so that should be there in the set already. Otherwise, so just think about this, right? 1, 2, 3, 4. When you are visiting 1, you are inserting 1 into the set. After that, you are visiting 2, you are inserting 2 into the set. After that, you are visiting 3, you are inserting 3 into the set. After that, you are visiting 4, you are inserting 4 into the set. Now fourth's next is 2, right? So you are, when you are checking for the next in the set, 2 is already there in the set, right? So basically this is where your loop will stop, and you will mark the next of 4 to be null. So solution in simple way, this is the most simple way, I believe. Like you can have a set, just think about this as you're visiting nodes in a graph, right? So this is kind of the visited array that you have. So you, whenever you are visiting a node, you are pushing it into the set, right? Set is just for searching, making the searching easier. You can definitely have a map instead of a set, if that makes more sense. Like you can definitely do something like this. Instead of having set, you can have a map, right? So map this, and what you can do is visited of car equals to true. You are just visiting a node, right? So you can just mark this node to be true, that it is visited. It is visited. Now here you can check for current of next. So if not visited, if you are not visiting, similar to what you do in a graph, very similar to that. I'll just write on this. I'll just write on this. So you can do cut off next, not visited cut off next, then if visited cut off next, sorry, if you have already visited cut off next, then cut off next should be null, and you should return from here. So basically let's take an example here. Let's try to understand this with an example. So I'll write an example here, right? So let me go to full screen mode. Okay, I'll write an example here, and yes, you have to include map here, not a set. So what we are doing is so see, we are starting, let's say we have the linked list like this: 1 2, let me just increase the size, 1 2 3 4, and 4 is connected back to 2, right? 4 is connected back to 2. Let me just show it like this: 4 is connected back to 2. Again, like you cannot actually loop on the values. You cannot you might think, hey, can't we just store the value of a node as an integer here, because node star, then node star, the pointer to a node, it makes more sense to store integers, right? So there might be repetition of integers, like you might have multiple occurrences of 2 here. Although it doesn't mean a new occurrence of 2, but it means that you are looping back to 2. There's no way to show a loop back here in the comment, so that's why I'm writing 2 again. So it is looping back to 2. So what exactly is happening, let's understand that. So we are starting off at 1. Current is initially head, so we are starting off at 1. So we are marking 1. For 1 we are marking it to be true, right? So let's just insert the values in a set. Let's say if it is marked as true, it is inserted in the set. So 1 is marked as true. After that we are doing current equals to current dot next, because visited of current of next, what is current of next? 2. Visited of 2 is not true, right? It is not visited yet. So what do? We come to this one, current equals to current dot next. So we are at 2 now. Now we visited, we mark it as visited, so 2 is marked as visited. And again, current of next is 3, right? Next of 2 is 3, so it is not visited yet. So it is not true, so it will come to this part, current equals to current dot next, and it will come to the 3, right? So now visited of 3 will be there. After that, similarly 4 will also come, right? Now 4 is interesting. Visited of 4 is marked as true. Now see this: visited of current of next. What is current of next? What is the next of 4? 2. 2 is already visited again, right? 2 is already visited, it is going to be visited again. And the first element that is visited again is the starting point of the loop, and the element that you are at is the ending point of the loop, or it is the ending point of the linked list. So what you should do ideally here is you should make this null. You should delete this connection and make this point to null, and you are breaking the loop basically. So current of next, you set it to null, and then you return. So that's why this is working. Is this clear, Aryan? Is this clear with you? Why is this working, or how is this working? We'll come to a better solution, but just let me know if this is clear with you. And if this is clear with everyone, just let me know if this is clear with everyone. So how is this working? Is this clear with everyone? Let me know quickly. Let me know quickly if this is clear with you. Okay, so we'll, as I'm not getting any response, I think it's clear with everyone. So what we'll do is we'll go to the next question. Sorry, next question more now. We'll go to the next way. The optimal way to solve this, right? The optimal way to solve this. So this is called slow fast pointer technique. So let's say we have something like this: 1, 2, 3, 4, 5, and 5 is looping back to 2, something like this. What do is we maintain two pointers. One is called the fast pointer, one is called the slow pointer. So we'll maintain the fast pointer with green, the slow pointer with red. Why is it called the fast pointer? The fast pointer is basically, it will move by two moves in a single move. Slow pointer will move normally like one step in a move. So fast pointer, after the first iteration, it will move by two places, right? So it will move by two places, it will come here. The slow pointer, it will come by one step, so it will come here. Now fast pointer, again in the next iteration, it will move by two places, so it will come here. So from here it will come here. The slow pointer will move by one step, that is, it will come here. The fast pointer again will move by two places, so the fast pointer is coming two places, that is, here it will come back. And the slow pointer will move by one step, that is here. Note that you might think, hey, they met here, right? They have met here, but actually they didn't meet here. What happened was the slow pointer was there, but the slow pointer will also be moving, right? We didn't account for that yet, so that's why they didn't meet yet. Now in the next move they will meet. Now just see the next move. The next move, the slow pointer comes to 5, the fast pointer will also come to 5, so they will basically meet. Now the algorithm is that if the two pointers, both the slow pointer and the fast pointer, are meeting again, then there is a loop. Right? There is a loop if they're meeting again, and that actually makes a lot of sense. Just assume that you do not have a loop. Your fast pointer is moving at a speed of 2x. Your slow pointer is moving at a speed of x. Just assume there are two cars, right? And the road is completely straight. So one of the car is moving at a speed of 2x, other car is moving at a speed of x. Both start at the same point. Is it ever possible for x to come catch up with 2x? Never, right? So it is only possible for x and 2x to meet only when there is a loop. That is, it is moving at 2x, it is moving at x, and they will eventually meet at some point. Now coming to the question, like you might think, hey, it might also happen that there is a loop, right? There is a loop, but they are never meeting. They are like always one position apart or something like that. They're actually never meeting. Can that happen? Actually no, they will always meet. Or you might think that it might take a lot of time for them to meet, right? It might take a lot of iterations along this. They can circle a lot for a long time to meet again, but that's not the case. Actually, why is that not a case? Just let's understand. Once both of them are in the loop, right? Once both of them are in the loop, let's say both of them are in the loop, if you see, it is moving by two steps at a time, and it is moving by one step at a time. If you consider the reverse distance means the distance like this. If you consider the reverse distance, the relative distance between them is always decreasing by one every move, right? Why is that? Let's understand that. So if we remember this, so let's say where was it? It was here, I believe. It was here. The slow pointer, the fast pointer was here, the slow pointer was here. What is the reverse distance between them? Reverse distance means this way. The actual distance is this way, the reverse distance is using the cycle this way, the other way around, right? So what is the reverse distance between them? The reverse distance between them is basically what is the reverse distance between them? It is basically right now 1 2. 2 is the reverse distance. After one move, what happens? This will come here, and this will go to the next place. So the reverse distance C has reduced to 1. Reverse distance has reduced from 2 to 1. So after every move, the reverse distance is actually decreasing by 1. So that's why after at least n, after at max n moves, they will definitely meet. After at max n moves, where n is the length of the cycle, they will definitely meet, right? So at every point their distance is reducing. Or you can think about reverse distance as the distance between the from the first pointer to the slow pointer, from the fast pointer to the slow pointer, whatever is the distance, that is the reverse distance, and it is actually decreasing by 1 every move, because the fast pointer is moving by 2v, the slow pointer is moving by v. So it is like it is or v is 1 here, so distance is reducing by v, which is equals to 1. So that's about the slow and fast pointer, about if we can detect if there is a loop. But that's not the question, we also have to remove the loop, right? We also have to remove the loop. How do we do that? So it tells that so this is the start, this is the point where they meet, right? I think 5 was the point where they meet. So we want to determine the starting position of the loop. So we want to determine the starting position of the loop. So this is the point where they meet, and we want to determine the starting point of the loop. So what we'll do here is we will remove one of the pointers. So let's I will not remove actually, so here one of the pointers will be there. We will move one of the pointers again to the starting, right? Again to the starting. And from here now, if both of them move by the same speed, that is the speed of 1, that is they move by one place at a time, they will meet at the starting point always. If you consider this example, in only one iteration, if you see, they will meet at the starting point. Both of them move by a speed of 1, and this will come here, and the red will also come here. So in one move, they're meeting at the starting point. And this is always true. This is always true. We'll take another example here just to understand better. So let's create another loop here. So let's say the loop is like this, right? The loop is like this. So what will happen here? Just see. First of all, we'll do the normal detection, Floyd cycle detection. So this is called the Floyd cycle detection algorithm, by the way. The Floyd cycle detection algo, right? This is the name is this. Okay, let's do the Floyd cycle detection algorithm. So the fast pointer will move by 2 places. So the fast pointer moves by 2 places. It will move to directly 3. The slow pointer will move by 1 place. It will move to 2. The fast pointer will now move by 2 places. So it will move to 5. And the slow pointer will move by 1 place. It will move to 3. The fast pointer will move by 2 places. So it will move to 2. And the slow pointer will move to 4 as well. So it will move to this point. So they meet, right? This is the point where they meet. Now, the second phase is that we'll move one of the pointers. We'll keep one of the pointers here only. The other pointer will move to the starting. And now both of them will move with the same speed, that is 1, right? Both of them will move at the same speed. So what will happen here now? After one iteration, 4, it goes here. And this will come here. So green will come here. And after second iteration, it will come here. It will come here. And the green will also come here. So see, they're again meeting at the starting point, right? They're again meeting at the starting point. So this is how it will work. We'll understand the proof for this. We'll definitely understand the proof for this. But yeah, let's just understand the proof for this. But again, like one thing to be sure about is in both the cases, although we saw that whenever it is reaching the starting point, the other pointer is also coming back to the starting point. But that might not be the case. There might be some of the rotations that are being made, and after that they're meeting. So that might be the case as well. As the cycle is small, that's why this is happening, right? So okay, let's understand this. Why is this working? So okay, let's say this is a linked list. This is the loop in a linked list, right? This is a linked list. This is the loop in a linked list. So the fast pointer, okay, the fast pointer is traveling by the speed of 2. let's say it covers a distance, let's say it makes y rotations here, right? It makes the fast pointer makes y rotations in this cycle before it meets, right? And it meet at a position of k from the start. So this position where they meet actually is k. So then it meets at a position of k, and before k it makes y rotations, complete rotations. So and this length is, let's call it m, right? So the distance, total distance traveled by the fast pointer is, the fast pointer travels a total distance of what? It will travel a total distance of 2 into, as it is moving by a speed of m. So right, uh, total distance, no, the total distance will not the same. The point, the final point will be same, right? Speed, uh okay, time will be same. So 2 into, it will take m plus, not sure why, the length of the loop, we, let's call it n. The length of the loop is n. This is total n, right? The length of the loop. So y into n plus k equals to, and for the slope pointer it will be m plus m plus k. It will be m plus k plus, let's call it x moves are done, xn, x rotations are done, x into n. So what will it be? It will become 2m 2k minus m plus k. So it will be m plus k is equals to xn minus 2yn, right? Xn minus 2y1, or x minus 2y into n, right? This is the okay. So this is the relation that we are getting, like they're meeting at the same point, right? So that's why. So m plus total distance traveled by both of the final point, uh, final point of meeting, or the time will be the same. So x minus 2y into n will be equals to m plus k, right? It will be equals to m plus k. This actually tells us that, this actually gives a very valuable information, that is m plus k is divisible by n. M plus k is divisible by n. What is m plus k again? M is the total distance from the loop, from the starting point of the linked list. K is the point where they are meeting, where the pointers are meeting, and n is the total length of the loop. This total length of the loop, it is n. There are n nodes in the loop basically. So m plus k is divisible by n, right? So let's write it down again. So it is basically m plus k is divisible by n, Now let's consider the second part. K, the pointer, the fast one of the pointers is already starting from k, right? The second pointer is starting from the beginning, right? Okay, so when it reaches the starting point, when the second pointer reaches the starting point, what is the distance traveled by the second pointer? It is equals to m, the total distance. So when the second pointer reaches this position, the total distance is travels is m, and the fast pointer will also travel the same distance. The fast pointer will also travel the same distance, because it is also moving by a speed of 1 now. Both of them are moving with the same speed. So if it travels a distance of m, the fast pointer will also travel a distance of m, but he will travel a distance, it will travel a distance of m from this position k, because it is starting at position k, right? So it is traveling a distance of m from the position k. So it is basically m plus k. It is basically m plus k, right? A total distance, like total deviation from this point, from the starting point. What is the total distance from the starting point for the second pointer? It is already traveling at a distance of k. It is traveling a distance of m more, so total distance will be m plus k. But we know that m plus k is divisible by n. That means m plus k is divisible by n. What does it mean? it will again come back here. Whenever it is m plus k, after every m plus k distance, it again comes back to the starting point. So basically they are meeting again at the starting point. So that's the proof, like why do they meet again in the starting point? Because m plus k is divisible by n. So the second pointer will travel a distance. It's already at a distance of k. It will travel a distance of m more from the starting point. So as m plus k is divisible by n, so therefore it is actually coming back to the starting point whenever this pointer comes to this starting point. That is m plus k, right? Total distance. So that's why they meet again. So let's quickly write the code for this, and let me know if it is clear with you. If the proof is clear with you, like why is it working? So let's quickly write the code. So what we'll do here, we can remove map. We can remove map, and node star past pointer equals to head, node star slow pointer equals to head. Now what we'll do here, we'll do while, why will it come to the starting point? Because m, once again, give me a second. Yeah, because m plus k is divisible by n, right? Let's just consider for the second pointer, right? M plus k is divisible by n. Let's understand this again. Okay, so this distance is m. This distance is m. The cycle length is n. That is, there are n nodes in the cycle, right? And they are meeting at the first time. They are meeting from this point. From this starting point, they are meeting at a distance of k for the first time, right? So now one of the pointers is here already. The second pointer is here, and we have already from the first proof, we have know that we already know that m plus k is divisible by n, right? M plus k is already divisible by n. This is what we already know. Now when this red pointer, both of them are moving by a speed of 1, that is one node at a time. When the red pointers comes at this point, the starting point, what is the distance traveled by it? The distance traveled by it is m. For this pointer, the red pointer, the distance it travels is m, right? It travels a distance of m when it reaches the starting point s of the cycle. It travels a distance of m, right? This is given as m. So if it moves by a speed of 1, it is definitely traveling a distance of m. Is that right? Is that right? It is definitely traveling a distance of m, right? Is that right? Yes. Very good. So this pointer is also moving by one step at a time, right? In the second part, it is also moving by one step at a time. So when this pointer reaches s, this pointer has also traveled a distance of m. The green pointer has also traveled a distance of m. What is the relative distance of the second pointer, that is this green pointer, from s? So it was already k units apart. It was already at a distance of k apart. It is traveling a distance of m more. So the total distance from s will be m plus k. When this reaches the starting point, it will be m plus k. But m plus k modulo n is equals to 0. That means it is making a full cycle. So it is coming, when the red pointer reaches this is also reaching this point. Does it make sense? If you have a cycle of size 5, this is the starting point, you have a cycle of size 5, you are 2 units apart, and if you travel a distance of 3 units from here, where do you reach from with respect to starting point? You reach a distance of 3 plus 2 modulo 5. That is again starting point. If you see 2 units you are apart, 3, 4, and you're coming back here 5. So you're basically coming back in a full cycle way. You're coming back to the starting point. So that is where they meet, right? So let's quickly look into the code for this. So while fast pointer fast pointer not equals to slow pointer, it will be so we'll directly go to head of next, right? So head of next, and we'll directly go here from, and let's add a conditional check here that if head of next equals to null, return, right? And also first pointer not equals to slow pointer, and first we'll have a additional condition here if while fast pointer not equals to null and fast pointer not equals to slow pointer. Till then what we'll do is fast pointer, if fast pointer of next is null, that means it doesn't contain a loop, so equals to null, so we'll return from here. Otherwise we'll do fast pointer equals to fast pointer of next, we are moving by a speed of 2, and slow pointer equals to slow pointer of next. Great. So we are done with this. So we have basically reached the meeting points, and definitely there is a loop, otherwise it would have returned. Right now there is a loop. So what we do, we move the slow pointer to head again. Right, slow pointer will move to head again, and we'll maintain another pointer here, node star temporary pointer, that will be pointing to the fast pointer. So that will be pointing to the fast pointer, right? So that will be pointing to the fast pointer. Just an optimization, otherwise you have to run one more loop. So that's fine. So while again slow pointer not equals to fast pointer, slow pointer equals to slow pointer next, temp equals to fast pointer equals to fast pointer next. So the purpose of temp is just to store the previous pointer, right? Because we'll meet at the first pointer again, first pointer of the loop, but we want to remove from the last node, right? We want to remove from the last node. We want to make it point to null. So that's why we have this temp. Now we can just do temp of next equals to null, and that will actually do solve our problem. So if we just do temp of next equals to null, we are done. So let's quickly see if this is working. Let me just quickly check the code as well. Compilation completed, your output is 1. I think this is working. Let's see. Okay, it is not working. Your code output is 0. Okay, we have 758, 36, 16, and 1. What is 1? Its correct output is 1. What is the output that we are expecting? Okay, linked list does not contain any loop. So it doesn't work when it contains doesn't contain a loop. Let's understand why it doesn't work. Head of next is null, will return. Fast pointer will be head of next dot next. Slow pointer will be head of next. So while fast pointer not equals to null, and so if fast pointer, here we have to add a condition that if fast pointer equals to null. So if fast pointer equals to null, we have to return here as well. So that's the condition that we have to add. Let's compile and test. I think okay, it doesn't work yet. Why is it giving a cycle here? Let's understand again. Fast pointer not equals to null, that's fine, and that's true. And fast pointer not equals to slow pointer, what do we do is fast pointer of next is equals to null, then we return from the function directly, right? If otherwise fast pointer equals to fast pointer of next and slow pointer equals to slow pointer of next. So fast pointer should be null, either should be null, or it should have returned null from here. uh, you should have written null from here. While fast pointer not equals to null and fast pointer not equals to slow pointer. So if one of them is false, it will break, right? If one of them is false, it will break. Slow pointer equals to head, temp of next, not equals to temp. Yes, okay. So node of fast pointer, slow pointer. Let's see for this example. So 7, 58, 36, 34, 16. So first of all, fast pointer is at first pointer starts at 36, slow pointer will start at 58. Now it will move to next is not null for 36, so it will move to 16. uh, it will move to 16 and slow pointer will move to 36. In the next iteration, from 16 it will see fast pointer of next is equals to null, right? So it should return from here, fast pointer not and fast pointer not equals to hmm, while fast pointer not equals to null and fast pointer not equals to slow pointer, that's fine. If fast pointer of next, am I making the condition, if am I writing and or these things, making some mistake there? Fast pointer not equals to slow pointer, it should actually go into this case, right? If fast pointer dot next not equals to null, reset code, what are the options there? Test against custom input, let's try this out. So 5, 7, 58, 36, 34, 16. I think I'm making a small mistake. Your output is 0. Okay, my output is 0. That's fine. Let's understand why it is 0. So we'll add some debugging statements. Maybe fast pointer not equals to null, it is not equals to null definitely. If it is equals to null, it should break. Also fast pointer not equals to slow pointer, it should not be equals to slow pointer as well. Head of next. Okay, so if fast pointer equal of next equals to null, it should come here, right? It should come here. So let's add a logging statement here. So see out here, and let's give a new line and return. Let's see. So compile and test. Let's compile and test here. Wrong test case, not sure. 758, okay, it's not coming here. So let's see why is it not coming here. So let's see out on the fast pointer, right? So see out will return from here. So see out value at fast pointer. So value at fast, or rather what is the node structure? So node structure will be data, uh, see out fast pointer dot update. I think there's some problem with my code only. It should not be wrong, the test case should not be wrong. Let's see. Fast pointer, but we have placed a condition, right? Of next is null. If it goes to null, it should break here only, right? So it comes to 36. Let's see. It comes to 36. It starts at 36. After that, it goes to 16. After that, it goes to 58, 34. Why is it cycling? Is the test case wrong? Okay, there is a loop, I believe. I think the test case is wrong. Interesting. I think the test case is wrong here. I'm not sure if we have another way to have this. Remove node in linked list. Remove cycle. think the test case might be wrong there. Let's see if we have something here. Same thing, right? It is the same thing that we are at. Interesting. Okay, I think this code should work. This code should work, but again, like it is. X is 0, output is 1. What is X? What is the value of X? If the linked list does not have any loop, X is 0. X is the position of the loop. Okay, X is the position of the loop. So, okay, let me try again. And what are we returning? What are we returning actually? Remove the loop if it is present. And what is the output? Output is 1. Acha, if the loop is present, if you remove it, it will successfully return 1. Okay, there is a loop. I think there's some problem with my code then. Let's run this again. uh let's see. So 7 8, there's a loop and it points to index 1. So 16 will probably point to 58, or it will point to 7. I think 16 will point to 7 or 58. So after 16 it will come to 758, it will come to 58. After that it will come to 34. So 16 is pointing to 7, right? It's a loop from 16 to 7. Now, okay, there's a loop and expected output is 1. We were not able to remove the loop then. That's fine. Let's see now what have we done. Okay, now we are maintaining 2 pointers, so slow pointers. So where are the meeting? Let's see the meeting point. So see out fast pointer dot of data, right? See out fast pointer of data, and let's print it in a new line and understand where are we meeting. So let's compile and run. Okay, we are meeting at 7. We are meeting at 7. Should we meet at 7? I'm not sure. Let's see if we should meet at 7. So let's click come here. Your canvas. What was it again? 758, 36, 34, 16. 758, 36, 34, 16. 36, 34, 16, right? So fast pointer, slow pointer, it will move by 2 places, it will move by 1 place. Let's keep on rubbing as well. Again by 2 places, it will come here, it will come here. So 2 places, it will come here, it will come here. So again by 2 places, so it will come 58, and it will come by 1 place, so 34, and again it will move by 2 places, so 34. Actually they are meeting at 7. Oh, I got it. So I think I made a mistake here. So 34, 16 and 7. Yeah, so it should come here and here. So this is the meeting point. 7 itself is the meeting point. So basically we are starting off at the same point again, right? And that's why it is not working. So if that's the case, we should remove the last node. If head equals to the pointer, that's something that we had forgotten. So yes, so if fast pointer equals to head, right? So if fast pointer equals to head, then we should go to the last node. So while slow pointer of next not equals to fast pointer, slow pointer equals to slow pointer of next, and slow pointer of next is null. Slow pointer of next is null, equals to null, and we should return. So this should actually work. Let's quickly test it out. Okay, it's working, so we can submit now. Yeah, we actually missed that case where they actually meet at head. So if they are meeting at head again, this will actually not work, right? Because slow pointer is equals to fast pointer. In that case, temp is already equals to fast pointer. There will be a problem. So we are not getting the last node basically, last node before pass pointer. So yeah, this is the code. Is this clear with everyone? How is this working? Is this clear with everyone? Let me know if you have any doubts. Let me know if you have any doubts with this, or is it clear with everyone? Any problems, or is it clear? Okay, I don't think you have any problems. So yes, we can end our stream here. So this was the problem that we wanted to solve today. And mostly these are all questions from Amazon interviews. So this is kind of an Amazon interview problem solving series. So we'll be doing it for a couple of days. We'll be solving some good questions that are there. So this was one of it, one of the most popular ones. Not only in Amazon, but in other companies as well. Similarly, every day we'll try to do one problem. So yeah, do join around this time only, and we'll be solving a problem every day. And thank you guys for joining in. Good night.